Hi, welcome back to another lesson in modern atomic theory. Today's lesson is called Electromagnetic Radiation. And if you take a look at the three pictures on the slide, just think about what do all three of those pictures have in common. And you're probably thinking something like, well, they all give off light. Maybe you're thinking you get warmth from them. And if that's what you're thinking, you're absolutely right. We can say this in a little bit more scientific way by stating that energy is being transmitted from one place to another by light in all three of these examples. So what in the world does that have to do with electromagnetic radiation? Well, that's a really good question. What is electromagnetic radiation anyway? And surprisingly enough, it is the exact definition that we just gave in our last slide. It is when energy is transmitted from one place to another by light. Below, if you look at the slides, there are some pictures showing different types of electromagnetic radiation, EM for short, electromagnetic radiation. I'll abbreviate it that way oftentimes. Here we have radio waves and microwaves, gamma rays being emitted by a potassium-40 atom. Here's X-rays everyone's familiar with. And here this person is absorbing all kinds of radiation, infrared radiation, visible light, ultraviolet or UV radiation. Those all come from the sun. And all of these are different examples of electromagnetic radiation. So now that we know some different types of electromagnetic radiation, what are some characteristics of them, of these different kinds of radiation? And in order to answer that question, we need to first learn a little bit about waves. Here are some wave characteristics that we need to understand. The first one is frequency. It's represented by the Greek letter nu. It kind of looks like a little lowercase cursive type of V. And frequency is just how many peaks pass a certain point per given time. So the units of this would be 1/seconds because it's the number of passing through per amount of time. And represented below, we have a representation of high frequency where we have many peaks passing per given time. And here is an example of a low frequency where there are not many per given time. The next characteristic is speed, which is, everyone knows that it's how fast the wave travels. Electromagnetic waves travel at the speed of light. So the speed of light is 3.00 times 10 to the 8th meters per second, and it's represented with a little c, and that's to distinguish it from other speeds. From electromagnetic waves, we're going to talk about the speed being the speed of light. And the last characteristic we're talking about is wavelength, which is represented by this Greek letter, lambda. Looks a little unusual, but that is how it is represented. And wavelength is the distance between two consecutive peaks. So here we have a wave, another wave, and the distance between the crest of this peak and the crest of this peak is 1 wavelength. Here we're going to discuss how frequency, wavelength, and speed are related. And they are related in this nice little equation right here. Speed of light equals wavelength times frequency, or C equals lambda nu, is another way you can remember it. Here, the relationship between frequency and wavelength are very important to note, and notice since they're multiplied together in this equation, the two are inversely proportional. So when one of them gets larger, the other one gets smaller in value. And if you want to think about that down here, I have a graphical representation of it. We have high frequency where many waves are passing through at a given time, and when that happens, there will be a shorter wavelength. Here, when we have very low frequency, we're going to have a longer wavelength. So it's important to remember that the wavelength and the frequency are inversely proportional to each other. So how does energy relate to waves? We know that if energy increases or gets larger, we're going to also see an increase in the wave's frequency. And here, again, if energy increases, we are going to see a decrease in wavelength. And you'll remember this from our last lesson, that with very large wavelengths over here, we have very low energy. And down here where we have very small wavelengths, we have a much greater energy. And this representation here is also a good way to see just where all of the different types of electromagnetic radiation fall in terms of their wavelengths. Here at the short wavelength end of the spectrum, we have gamma rays. They're packed with high energy, they're low wavelength. Up here, radio waves are some of the lowest energy, and they have very long wavelengths. And you can see all the other different types of electromagnetic radiation falling in between those. Now, this lesson would not be complete if we didn't talk about one more thing. Here, we are going to ask the question now, the age-old question, is light a particle or is it a wave? Which is something that's a curiosity to people over long periods of time. We've been talking about light as a wave, but we would be completely remiss to not discuss that light is also a particle. And how can that be? It is the wave-particle nature of light that is a special property of light. It's just very unique. And when we do discuss light as a particle, we discuss it as individual photons or little packets of energy. That is how it transfers energy from one location to another, is through photons. So that does conclude our lesson, and if you'll go to the wait for the next slide, you'll be able to see some different ideas for achieving advanced proficiency. Thanks, and we'll see you in class.